over here, mathematical modeling. So this one we already learned in the previous lesson, explain mathematical modeling. Just want to ask you back, do you still remember what is the definition of mathematical modeling? Still remember? I need to jot down. Also, I need to make you familiar with the definition over here. Mathematical modeling. What is a mathematical modeling? It is a representation of you need to get a system or scenario. After that, that is used to gain what? This is very important. Yes, qualitative and or quantitative. Quantitative what?
Understanding.
Yes, understanding of some real world problem. The whole line is important. This part, quantitative and or qualitative, qualitative and or quantitative understanding of real world problem, and to predict what?
Future behavior.
Yes, future behavior. You remember all these main points. Usually, I think this part, they will come out maybe in the objective question. They will ask you which one is the definition of mathematical modeling. So you have to identify these 3 points. It is a representation of system or scenario that is used to gain qualitative and or quantitative understanding of real world problem to predict the future behavior. These 3 points over here. Okay, so we continue on 8.1.2. Today, this is what we are going to learn. Solve real life problem through mathematical modeling, which involve the following functions. First one, linear function, and then quadratic function. These two you have learned. And the next one is exponential. And communicate the mathematical modeling process implemented. So actually, when you come up with a mathematical modeling, not only linear, quadratic, and exponential, you might have all sorts of graph that you have learned before, like reciprocal, you remember, the cubic graph, and so on. So actually, this 3 is the main thing that you have to learn. After that, you are going to apply it on how to solve the problem and come up with your own mathematical model later on. Okay, let's see. Today we are just going to go through one example only. After that, I want you to try to do the group work. Okay, this is the one from your textbook. How to solve real life problems through mathematical modeling. Okay, the aim is to apply mathematics in problem solving. So you look at the steps over here. Based on the information and diagrams given, determine the type of function, either linear, quadratic, or exponential, that may be used as a model for the data, and you discuss your selection. So for first one, we discuss together. Number 2 here. A doctor uses the data to study the resting pulse rate of a normal adult according to the number of hours of exercise per week. So you can see the graph over here representing the resting pulse rate in beats per minute. Okay, after that, numbers of hours of exercise per week. So you can see the data with the dot over here, meaning the more number of hours exercise per week, you can see the more number of hours, the resting pulse rate is lower. Okay, and then they have this, what do you call this? Do you understand this one or not? Do you know what is this? I ever saw somebody use this before in the graph that we learned. I think it's Ayman. This is a squiggle. You know the function of squiggle? The squiggle is, you don't know. The squiggle is used to indicate there is a gap in between that you have to start with a number that is very big. For example, of course, if you exercise more than 9 hours or 10 hours, your pulse rate cannot be lower than 45, right? Somebody, a healthy person, cannot be lower than 45, or else you have a health problem already. That's why they have a squiggle over here, okay, to indicate that actually the normal one start from 45 up to 85, and then it cannot be more. Like if it is a lot, your beat per minute, it's also a very dangerous situation, dangerous scene over there. Okay, so now if you look at the graph over here, look at the plotting point. Can you tell me this one is under which function? Either linear, quadratic, or exponential? Any idea? Can you imagine?
Is it linear?
Yes, correct.
Exponential.
It is actually linear. It cannot be exponential. Okay, linear. Can it be exponential? Might be also. Might be. So, for example, we take an example. If you exercise less than, no, let's say we take this at the back. If you exercise more than 10 hours, 11 hours, 12 hours, can you imagine what will happen to the resting pulse rate? Is it going to be lower than 50, lower than 45 over there? Or if I extend, wow, when you exercise for 13, 14, 15 hours per day, 16 hours per day, it could be exponential. But over here, because of the data is plotting like that, right? It looks something like linear actually. Okay, it could be exponential. So we carry on. Let's look at the second graph here. A scientist uses the data to study the population of tigers. So you can see from the year given, from 1960 to 2020, okay, with the population is getting less for the tiger. It's moving down. Okay, what types of graph is this? The shape is quite clear for this one, isn't it?
Exponential.
Yeah, this one is exponential. But if we don't take any action to avoid the extinction over here, what do you think the graph could be? For example, you don't, there's no action taken for taking care of the animal, and then there is a very 2022 they hunt the tigers without control. 2023, 2024. Oh, I have to follow the scale. The scale is 10, 2020, 2030, 2040, 2050, 2060. So you imagine, could there be any more tiger in 2060? If there's no action, if there's no action taken, it could reach 0, right? So it might be a linear graph, but so far right now is an exponential graph. Okay, now we look at C. A marketing manager studies the data which shows the relationship between the profit and the numbers of years a product is in the market. So this is the number of years, okay, first year, second year, third year, fourth, fifth, and sixth years. And then the profit in millions. So first year, the profit is very little, about 3 million. And then second year increase, third year increase, fourth year is the highest, and then it goes down again. So what kinds of graph is this?
Quadratic.
Yes, correct. This is a quadratic graph. It goes up, after that it goes down after a certain time. Okay, so this graph, it shows that we can determine the type of function that may be used as a model for data by studying the graph pattern. Okay, now we move on. From the graph that you identified just now, I move everything to the left here. So you can see the first one we assume is a linear function. What is a linear function? It is a graph that resembles a straight line. So this one you already know. After that, the quadratic function, the last one here. Hopefully you can see. Quadratic function is a curved graph in the form of parabola. So the curve may rise and then fall, or fall and then rise. So it can fall first and then rise also. So it's a quadratic function. Whereas for the second one here, I assume because it looks like an exponential function. Okay, so for this exponential function, there are a few things that you have to know. It is a curved graph illustrating an increase or decrease in values of data at a sharp rate. And the exponential function can be written in the form of equation y equal to ca to the power of x. A is a positive real number, but then it cannot be 1. Why? Because the answer, it will different from what we have later on. C is the initial value. We are going to see this later on, how the C become the initial value. For example, if C is equal to 1, A is equal to 2. So you can see C is equal to 1, A equal to 2. 1 times 2 is equal to 2, right? So over here, y, you can get the graph of y equal to 2x like the one in the diagram. This is not the 2x, like, let me see. Yeah, this is the, sorry, my x is not correct. It's 2 to the power of x according to this. Okay, this is 1 times 2, so we get 2x. So you can see the graph on the right over here. I'll make it bigger for you. Okay. So again, we go back to what we have just now. C is the initial value. So you can see over here, C is actually 1. That is the y-intercept over here, the initial value. Okay, and then when A equal to 2, so 1 times 2, you get a 2 to the power of x. So you are going to get an exponential graph like this. Okay, this is the formula for the exponential graph. Okay, we move on. That is what we are going to learn today. We are going to see the situation or the scenario for an exponential graph. Okay, number 4. I jump to number 4 first. We go back to the second and third one in the next lesson. So this is what you have learned in Form 3 actually. I take this as an example so that it's easier for you to understand. Okay, we look at this one. Compound interest is the interest that is calculated based on the original principle and also the accumulated interest from the previous period of savings. At the beginning of a year, Mr. Gomez saved 20,000 in his savings account with an interest rate of 4% per annum. Do you still remember what is a compound interest? Still remember?
Interest multiple times per year.
Yeah, correct. We have compound interest and the other one is a simple interest, right? So this one is compounded a few times a year. Okay, so when he saved 20,000, meaning that this 20,000 is the principal with the interest rate of 4% per annum, meaning that 1 year is 4%. And the interest is compounded once a year. So this one is easy, only once a year. It means every year you just add on. And then they ask you to derive a mathematical model for Mr. Gomez's total savings after 3 years of savings. Solve this problem through mathematical modeling. So through the mathematical modeling, you have to go through all of this. I'm a very robust robot. So I identifying and defining the problem. So over here, you have to identify and define the problem. So I already highlight everything over here, meaning that these are the information given. So actually, you just need to mention all of this in your answer later on for the first part, identifying and defining the problem. Okay, first one, you can see this 20,000, meaning this is his principal of 20,000. And then the next one, the interest rate is given. So the yearly interest rate is 4%. This is the second point. And then the third one, the interest is compounded once a year. This is another point here. After that, this is the question. Derive a mathematical model for Mr. Gomez total savings after T years. So you have to get a mathematical model after T years of saving. Okay, so I related it to this part over here. Everything is from your book. You can read at your book also here, first part. So you can see, they just beautify the sentence only from the question given. Okay, the first one, Mr. Gomez is given compounded interest, which is a compound interest, which is compounded once a year. Up to you how you write the sentence, as long as you mention about it is compounded once a year. This is the important points. Okay, his principal is RM 20,000, and then the yearly interest rate is 4%. So the question derive a mathematical model for Mr. Gomez's total saving at the end of T years. Okay, after that, make assumption and identifying the variable. So this is the second one. Okay, this part, the making assumption and identifying the variable, not much of the variable, so they just combine both of it together. When it involves a lot of variable, you are going to separate these two. So making assumption, assume Mr. Gomez did not withdraw or raise his savings throughout the period of saving. If he withdraw, then the calculation will be mixed up already. You won't be able to get the correct answer. So you got to assume he did not withdraw or raise or increase his savings throughout the period. Second, this part is the variable, identifying the variable here. The variable are the principal amount in RMP. So you have to think of an appropriate alphabet to represent it. Like this one, because you learned in Form 3 already, so you already know how to represent the principal. Principal, we usually use P. Yearly interest rate is in R. Number of times the interest is compounded, that is represented using N. And the time, T years. Okay, so we have altogether 1, 2, 3, 4 variables involved. Okay, so I am a very robust robot, so I am a. Okay, we follow the third one right now. Applying mathematics to solve problem. So this part you have to find out the answer already after T years. How much is the total savings? So you are going to come out with a calculation like this here. Keep in mind that when calculating the compound interest, each year we have 100% of the principal plus 4% of the previous balance. So we construct a table as follow like this. Okay, this one up to you. When you write down for a mathematical modeling, if the person who read already understand this part, then you don't have to explain. If you want to make them understand better, then you explain all of this lah. Okay, so this table is divided into 5 columns. The first one is the year, followed by the principal. After that, the interest received, principal plus interest, and the amount of savings after the first year. So the principal that we know earlier just now, it is 20,000, isn't it? I'm gonna make it smaller. Okay, 20,000. So interest received, we know that the interest is 4% of the previous balance. So what you do is you are going to multiply the 20,000 with 0.04. That is the 4%. Okay, after that the principal is 20,000 plus the interest. This is the interest here, that is 20,000 times 0.04. Okay, so when you look at this 20,000 plus 20,000 times 0.04, this is like the 4 types of rule that you have learned in Form 1, the distribution, the law, the distribution law. Hopefully you still remember. So 20 plus 20 times 0.04, you can simplify it, becomes 20,000 times 1 plus 0.04. Why? Because 20,000 times 1 is 20,000. After that, 20,000 times 0.04. So this is what you have over here. It's the same thing, they simplify it. So the amount of savings that you have will be 20,000. You copy down. And then this part 1 plus 0.04 will be in bracket 1.04. That is how you get the first one. Okay, so this is the amount of saving at the end of the first year. Then you are going to continue, copy down this, put it in front here as the principal because your money already increased. So it's 20, I miss out 10 here, 20,000 times 1.04 will be your in principal. So now your interest is from the principal multiplied by 0.04. Therefore, it will be 20,000 times 1.04, that is your principal, times with the interest 0.04. Okay, then we are going to get the principal here. The principal is how much? That is 20,000 times, it's getting more, 20,000 times 1.04. We take it from the principal in front here. So this is the principal plus, you just add on the plus, the interest is this. So you copy down everything over here. That is the 20,000 times 1.04 times 0.04. So from here, this line that we have, we are going to simplify it. Simplify the back first because this one already simplified. Okay, so this one we copy down first. It is equal to 20,000 times 1.04. After that, you see plus 20,000 is a repetition over here. 20,000 times 1.04. So it's the same thing. Means this part we can just put it as a 1. It's the same as the principal. So we just put in bracket, it is a 1, and then you plus with 0.04. Okay, after that you check one more time. So you can see 20,000 times 1.04 is the first part. 20,000 times 1, we get 20,000. 20,000 times 0.04 is this part here. 20,000 times 0.04, this part here. Because 20,000 times 0.04. Okay, this is 1.04. Are you okay so far? After that, we can simplify this part. Can So we are going to simplify this part. 20,000 times 1.04 times 1. After that, plus 0.04. So we are going to get 20,000 times 1.04 to the power of 2. How to get that? Because this is 20,000 times 1. Okay, I simplify down here. We get a 20,000 from here times 1. After that, 1.04 times 1.04, this part here is 1.04 times 1.04 actually, because 1 plus 0.04. So we will have 1.04 to the power of 2. Okay, so we will have that over here. That is 20,000 times 1.04 to the power of 2. So they keep continue. This will be the principal now. Then move it to the front and keep counting the interest. Add on the principal with the interest. So you are going to get it like this. So continue until the 5th year. So you can see for the first year, this is the amount. For the second year, this is the amount. For the third year, they just follow exactly the same. So when it is like this, exactly the same, you can come out with your mathematical model already over here, your formula. So this part, applying mathematics to solve problem, we already solved it. We just need to continue with the next one. I am a vary. So vary is verifying and interpreting solutions in the context of the problem. So based on the table that we have above, at the end of every year, the amount of saving is a power of 1.04 times the principal. 20,000, and the power corresponds to the number of years of saving. It depends on how many number of years, that will be the power of it. So we can generalize this pattern to a mathematical model by letting P will represent the principal of the saving, T will represent the number of years. So you can see here, T represent the number of years, P is the principal, and R represent the yearly interest rate. Hence, the mathematical model is AT. This is the amount of savings after T years, equal to P in bracket 1 plus R to the power of T. So they ask you to note that over here, 1.04 is 1 plus 0.04. This is the one that we have just now, the red with the original amount, the principal, 1 plus the red. Okay, so this mathematical model is an exponential function that allows us to calculate the amount of savings if the interest is compounded once a year for T years. The graph on the right shows the exponential function. So this is a graph that is AT equal to 20,000 times 1.04 to the power of T. So remember, this one represents the C. C is the initial value. That's why you can see your graph with your initial value right here. This is your graph. AT is equal to 20,000. That's the initial value, the principal, times 1.04 to the power of T. So you will have a graph like this. Exponential graph. Okay, I continue. So you just read through here. The graph of the amount of saving after T years, the amount of saving after T years, AT, it shows an exponential growth as time T increases. So after V, I am a very robust. R stands for refining the mathematical model. So over here, when you want to refine it, you will ask your question. You will ask a lot of questions whether your formula can be used or not, and so on, and anything will affect it or not. So over here, to refine it, you see the mathematical model AT equal to P1 plus R to the power of T is used for annual compounding. In reality, interest is often compounded more frequently. For example, compounded semi-annually or quarterly. Semi-annually meaning half a year. This one, a quarter meaning 4 times a year. So if the interest is compounded monthly, the interest rate is divided among the 12 months because 1/12 is the rate applied each month. So the rate over here, you are going to divide by 12 if it is compounded monthly. The variable T in the exponent is multiplied by 12 because the interest is calculated 12 times in a year. So over here, you are going to add on a 12. So your model becomes like this, R over 12, and then this one you add on the 12 over here. So in general, if the interest is compounded n times per year, the mathematical model is AT equal to P1 plus R over n times to the power of NT. So actually they refine already the mathematical model, meaning that it can be used for no matter whether it is compounded once a year or compounded monthly or compounded quarterly or compounded semi-annually. So all of the this formula can be applied for all of the situation. Okay, then lastly, report the finding. So over here, you just need to write a full report following the above modeling. If there is no weakness, so you don't have to write anything for your report. The report actually is for you to use symbol and diagram to illustrate everything, and then you identify the strength and weaknesses of what you found out. After that, you think about it whether you can use this model to solve other example or not. If there's no problem, then your report is just very simple. If there is a problem, then you have to go back to what we have learned in the first lesson. You are going to list down what could be the problem and so on. Okay, so this is all about example 4. Do you have any question, class? Any questions so far? No?